This video is on composition of functions and what the domains and ranges look like of compositions of functions. So this figure shows two linear functions, f and g, and I've already put the domain and range of these on the screen. And so what we can see is the domain of f are all the x values, and the range of f are all the y values that we get in this particular thing. Now, these functions, if I had f of x, I could write it as negative x plus 7. I could have a linear equation. I could write it as a linear equation. And this one I could write as 1/2 x minus 1. However, remember that these, even though if I extended them, it would be clear that those are what the functions are. In this particular case, they have restrictions. Okay, so these linear functions have restrictions. So even though it could continue, the restrictions kind of cut those off. And so because we have certain things that are restricting f and g here, what we're going to do is we're going to take a look at what it actually looks like for f and g to be combined together in some way. And so let's say we have f of g of x. That means we're going to find the value of g first, just like we learned in Algebra 2. Then we're going to find f of the answer. So let's take a look. When x is 1, g doesn't have any value. So there's no value there. So there's no value that we can plug in. So there's no value of f of g of x because there was no value that we could plug into g in the first place. Now let's try 2. If I plug 2 in, I get 0 for g. That's this point right here. So then that's going to be the new x that I put into f of g. So 0 is my new x, and, well, there's no value of f. If it was a full function that had negative infinity to infinity as its domain, then that would have something. But I have nothing that makes that work. So once again, there is no point on f of g of x for x equals 2. At x equals 3, g of x is 1/2. That will now be the new x value that I plug, and once again, I can't plug it in because there is no such value on f. So because there's no value on f for 1/2, that means that I don't have any point on the graph. When I substitute 4 into g, I get 1. That's that point. So then that's now my new x value. So I'm going to look at x equals 1 on f, and I get 6. So if I'm looking at f of g of x, I finally have my first point. The first point that I have is the point 4, 6. And so I'm going to put 4, 6 on the graph of f of g of x. Now I can continue with this, and I'm going to do this pretty quickly. 5 gives me 3/2, and then when x is 3/2, I substitute that in to f, I get 5.5, or 11/2. So 11/2 will be on my new graph. And since these are linear, this isn't that hard to figure out what's happening. One of the big things that we do need to be aware of, though, is that whatever g of x is becomes the new x value that goes into f of g of x. So I'm going to fill these out, 5, 9/2, and 4. And so I'm just going to plot these points, and what I see is it ends at 8, 4. Since it's a line, it's pretty straightforward, no pun intended, line straight. But we end up with this as my f of g of x. So f of g of x, the domain of f of g is 4 to 8. And the range of f of g is 4 to 6. Now, one of the important things is g was the first thing that I substituted in. So I had to have the domain of G is originally what I started with. So I can't be anything less, or I can't be anything more than what I started with. I definitely have, like, the domain of f of G has to be somewhere in 2 to 8. But notice it got restricted even more. So we'll talk a little bit more about the restrictions that are happening later. But what we need to notice is that the domain of f of G is 4, 8, and it is smaller or more restricted than the domain of G of X. So that's something that we're going to keep in mind. All right, now let's do this another time. So if I'm looking at, let's choose this color. So for G of F, what we're going to do here is we're going to now substitute things into f of x. So one thing we'll notice is that there is no values for f of x on anything bigger than 5. Because if we look at the domain of f, it's from 1 to 5. So if I tried to plug in 6 or 7 or 8, I wouldn't get anything. So I already know that those are not points on the new graph of g of x. So if I substitute 1 into f, I get 6. That becomes the new x value. So once again, this point, the y value on f, becomes the new x value when I substitute it into g. So now I'm going to do g of 6, and g of 6 is 2. So 1 comma 2 is going to be on my new graph of g of f of x. Now I'm going to continue doing this. When I substitute 2 into f, I get 5, and so on. 3, I get 4, 4, I get 3, 5, I get 2. So those now become the new x values that substitute in to g. So now I'm going to do g of 6, I got 2. G of 5, I get 1.5, or 3 halves, and so on, all the way down. So these are now the final y values on my graph. And so when I look at this, I have all the points 1 comma 2, 2, 3 halves, 3, 1, 4, 1 half. I get this line. And so this line ends up being g of f of x. Now again, it's a restricted domain, but the domain is exactly the same as f here, because I started with f, or the domain of f, and then it ended up where everything that I substituted in gave me a range value that became a new domain value, a new x value, such that I got a point on g of f of x. So g of f ends up working out. The domain ended up being 1 to 5, which was the same as f of x. And so now here's the big takeaway for domains. I've already typed it out to try and make it as quick as possible, but the domain of some function, f of g of x or g of f of x or whatever, consists of all x's in the domain of the inside function that also make the range of the inside function be a part of the domain of the outside function. So if you substitute something in from the domain of the inside, and it gives you a range value that is able to be in the domain of the outside function, that value is okay. But if it doesn't give you something that is now in the domain of the second function or the outside function, that now has to be eliminated from the domain of the composite function. So this is kind of what's happening here. I take a value for x, I substitute it into the inside function, and then whatever I get goes into this new composite function. So if we look at it in terms of domains and ranges, the domain of the first gets plugged in, and out comes the range of the first. Then the range of the first gets plugged in to f, or the outside function, and then I have to look at the range of the outside or the inside and the domain of the outside. And it has to be the most restrictive of these two things. The most restrictive. So if, for example, the range of G is 1, 7, and the domain of F is 2, 11, where do these things overlap? What is the most restrictive of these two things? The most restrictive of these two would be 2 to 7, because 2 is included over here, 7 is included over here, but anything above 7 can't work here, and anything below 2 can't work. I'm sorry, anything above 7 can't work here, and anything below 2 can't work here. So that's kind of like the restrictions. Then what I do is I look at this function, G, and what I end up doing is I say, what can I plug in here to make this the range of G? And whatever that is my new domain. So whatever I can plug in here to make this work. So it's at least as restrictive as the domain of G. So this is a good starting point, but it can be even more restricted than that. And there's no real magic formula for determining the domain of the composition. You kind of just have to look at it, see what happens, but make sure that you take into account the original domain restrictions, because it's at least as restrictive as the original. Let's analyze 4 examples. F of G of x, I will take f of root x plus 9, and that gives me root x plus 9 squared minus 6 root x plus 9, which is x plus 9 minus 6 root x plus 9. So that's f of G of x. Now, if I take a look at the domain of f of G, I look at the original domain, which is negative 9 to infinity, and that takes me to the range of 0 to infinity. If I analyze how they compare, the range fits entirely in the domain, which means that even though this has to be restricted, when I substitute in things from 0 to infinity into this function, what's going to end up happening is I'm still going to get the entire range coming out. And that means that I don't have to restrict this domain at all that I had originally. So the domain of f of G is negative 9 to infinity. G of f, that's G of x squared minus 6x. So that's the square root of, if I look at this, x squared minus 6x, I can just replace x with x squared minus 6x plus 9. This factors to x minus 3, the quantity squared. So if I have x minus 3, the quantity squared, inside of a square root, what I end up with is the absolute value of x minus 3. Now, why does it become the absolute value? Because the inside of this can never be negative. So that means that when I take the square root of x minus 3 squared, if I had some kind of negative number on the inside, the squared turns it into a positive. And so I have the absolute value of this. So that's G of f of x. Now, if I look at what's happening, G of f of x, if I look at the original domain, negative infinity to infinity, that's still going to be the case in this. And if you look at the range and domain, they are exactly the same. So I don't have any issues with my domain and range. So my original domain is allowed to stand, negative infinity to infinity. So h of x being x squared and g of x being root x plus 9 will take us into our next set of 2 examples. G of h is g of x squared. So then I'm going to replace x with x squared in g. So this becomes x squared. So it's root x squared plus 9. Now, if I look at the domain of H, that's negative infinity to infinity. So it has to at least be restrictive as all real numbers. So I know that's not too restrictive. Now, if I take a look at 0 to infinity, that does shrink this a little bit. And it does shrink the range a little bit of what would eventually become the range in my new function. But that doesn't restrict my domain at all because I can still plug in negative infinity to infinity. And that's pretty clear from even just looking at this. I can plug in negative infinity to infinity, and that's not too big of an issue in that particular case. So the domain is negative infinity to infinity. The range is only 3 to infinity, but that's the domain. Now, if we take a look at h of g, that's kind of the reverse process. And one thing to keep in mind is that this, with the squared on the inside of the square root, becomes absolute value of x minus 3. This one, where the squared is on the outside, it does not become the absolute value of x minus 3. This is just a line. But this line has some interesting properties. So if we take a look at root x plus 9, root x plus 9 has a domain of negative 9 to infinity. If I look at the range, when I compare it to this domain, restricts what's happening in my new domain. So my new domain has to be restricted to 0 to infinity. So when I look at what's happening, I end up with only the right side of the parabola. Only the right side of the parabola if I substitute these things in, which means that I'm still stuck with only negative 9 to infinity as my domain. And that's kind of important to keep in mind. In none of these examples did I have any extra stuff that got taken out of the domain, but this one's really important for the perception of I can't just look at what I get at the end and think that I have no domain restrictions, because normally when I see x plus 9, I think no domain restrictions. I have to always keep in mind the original thing that I plugged in. I have to at least keep that as the restricted domain. That is the biggest domain that I can possibly have. The next video will go through a lot more examples that are a little bit more complicated.